Hello, everyone. Today we are continuing our mini series of introduction in concurrent programming by Nikita Koval, who is a researcher in the JetBrains. And Nikita, welcome.
Thanks, Dmitry, for the welcome words. Hi, everybody. And today we will have two talks, and now this is the second talk of the mini series on the introduction to concurrent programming. Today we'll talk about modern queues and the flat combining technique.
Okay, Nikita, I think it would be useful if you will summarize the previous topics that were covered in the first part for our listeners who joined on the second.
Oh, that's exactly what I planned to do in the beginning of my presentation, but let's do it now, for sure. And yesterday, in the previous talk, we discussed the most fundamentals definitions and algorithms in concurrent programming. So we first of all discussed how to build concurrent algorithms using the mutual exclusion using logs. After that, we extended this design for non-blocking algorithms. So we discussed how to leverage the atomic compare and set instruction. And we talked a lot about progress guarantees of concurrent algorithms such as log freedom and wait freedom. And we also talked about correctness in the world of concurrency, which is by default linearizability. And the main focus was on two state-of-the-art trace stack and Michael Scott queue algorithms. And we did all of these in just 1 hour yesterday.
Okay. Also, I would encourage our listeners to ask questions in our Telegram chat or in other interfaces. And we will warn you that we don't have a discussion after this part, but we will have summary discussion zone after this last part of the mini-series later in the evening. So don't hesitate to ask questions. If we would be too generous to discuss in the middle, we will just sum up them to the discussion zone or on the end of the presentation.
Yes, please ask all questions once they appear. Don't wait for any specific time in the presentation, because we have a small lag between the transaction and UC and VC. So if you ask questions in advance, it's easier for us to answer them.
Okay, so I think we are ready to begin. Let's start.
Let's start. So today is the second talk in the mini series, and we'll talk about queues first of all. So yesterday we discussed the classic Michael Scott queue, which is used almost everywhere. So you can check the standard Java library and the concurrent linked queue implementation. It's essentially the Michael Scott queue, and so kind of the most fundamental algorithm. But it's not the fastest one. It's not the most scalable one. And today we'll talk about building a really fast, really efficient queue algorithm. And after that, we talk about flat combining technique, which can transform any sequential algorithm to quite good concurrent version. So this technique in practice, it's usually much better than coarse grained blocking with the mutex we discussed yesterday. Okay, so this we already discussed what was yesterday. So we'll talk about queues first of all, And in order to make a really efficient SQL algorithm, we'll need a new primitive. So yesterday we used only the compare and set atomic primitive, and today we'll also use fetch and add primitive. And fetch and add, what it does, it atomically increments the counter by the specific address. It increments it by the specific delta and returns the value right before the increment. Okay, so it's kind of for example, fetch and add some address 1 is essentially an increment like plus operation, but it's atomic version. And when we design an algorithm that uses compare and set for synchronization, we usually have an infinite loop. We read the state. After that, we decide how we want to update the state. And then we update the state or the data structure using the compare and set instruction. So one thread updates the state successfully, and other threads they must restart because the cast fails, the state is already changed. So they start from the beginning and try to apply the operation again. And with the fetch and add, we can make synchronization more scalable because fetch and add is an unconditional primitive. It always changes the counter by the specific delta. It just returns the value that was before the increment, right? So we don't need to have this infinite loop. The idea that we apply fetch and add, so we know the previous value, we know the delta, and based on this information, we do the synchronization. That's the idea. And importantly, if you want to make a non-blocking algorithm, it's impossible to make it only on fetch and add. The theory says no way. But in practice, it means that we perform the contended part of the synchronization, leveraging the fetch and add instruction. And after that, we use compare and set. We use it to guarantee correctness, and in some corner cases, we do need it. But this compare and set that we will use, it will almost never fail. So the main synchronization will be performed via fetch and add instruction. And there were two great papers on how to build really scalable queues that leverage the fetch and add instruction. Both papers were published at PPOP conference. It's an academic, but a practical academic conference. And I will give you the intention on how these queues are designed on the higher level. So we'll not talk about some complicated parts, and in practice we don't need them. So, but we'll just build a queue that uses the ideas from these two papers. And first of all, we say the following: let's have an infinite array. Of course, we don't have such a construction in practice, but for simplicity, now we assume that we have it. We have an infinite array, and it will simplify the design a lot. And so here are the array indices in the bottom left corner, and the cell values are in the cells. So the structure of our queue on this infinite array is the following. We have the infinite array in which we store the elements. And we also have two counters, two infinite counters, because we have infinite array. And these counters point to the cell for the next deque request. This is deque index counter. And for the to the cell for the next enqueue request. This is enqueue index count. So in this case, when enqueue and deque counters coincide, then the queue is empty. So in this state, the queue is empty, and previously there were 1 and 2 added to the queue, and after that extracted. Okay. So the structure. So we have infinite array. We have two counters, and these two counters, they must be infinite, right? But if they are 64-bit counters, in practice, they never overflow. So in practice, 64-bit counters are infinite. That's one of the main tricks in designing such algorithms. And the enqueue-deque operations are very simple. Enqueue operation increases its counter. Thus, it claims the array cell for the operation, and after that, it puts the element to this cell. And the deque operation, it also increases its counter, the deque index counter, and it returns returns the value located in the corresponding in the corresponding cell. So how does it work? So here's enqueue. When enqueue comes, it first increments the enqueue index counter. Then it puts the element and finishes. After that, when deque comes, now there is no concurrent. There is no concurrency, right? So it's the same thread. So when deque comes, it increments the deque index counter and reads the value located in the claimed array cell. And for simplicity, we also now assume that deque is never invoked on empty queue. We'll fix this later, but now we just assume it, okay? So when we invoke deque, we guarantee that the queue is not empty. So maybe if Dmitry, you have questions, we can stop for a couple of minutes.
No, we don't have any questions so far, because I think maybe we didn't mention too complicated issues for a moment.
So I really hope that everything is clear for now, so we can move forward. Let's try to move forward then. So now we want to make this algorithm correct in the concurrent environment. And to do so, we simply replace the non-atomic increments. So remember the previous slide. You see the previous slide? I hope you see the previous slide. And these are just enqueue index plus plus, deque index plus plus. They are non-atomic. And now when we replace them with speech and DATs, these increments are atomic. And thus, when multiple threads perform enqueue and deque operations, we now can guarantee that with this, first of all, both enqueue and deque, they process array cells step by step, and also we guarantee that at most one enqueue and one deque is working on the same cell concurrently. Because at most one enqueue can work with the specific cell, and at most one deque can work with it. Okay, so don't really have a lot of concurrence, but still we have. So, due to the fact that our world is concurrent, and now we have two threads, for example. So we have the yellow thread, which will perform enqueue, and the purple one that performs dequeue. They will, this enqueue and dequeue will lead to a nice conflict, actually. So let's see the problem. When the yellow thread performs it increment, sorry, here it should be fetch and add, of course. Sorry for that. So it should be fetch and add enqueue index, and after the yellow thread claimed the slot, it has not put the element into the corresponding array slot. And if after that dequeue comes to work on the same slot, so dequeue increments the dequeue index, so now it should work with the array cell 0 as well, but this slot is empty. And as this slot is empty, it can't proceed. So if it returns the value located in the cell, it will return null, but why null? It was never enqueued. And here is a problem. To solve this problem, we can add a very simple workaround. We can make our algorithm blocking. We can make dequeue wait until the slot becomes non-empty. Because in this situation, we do know that there is an enqueue that will come in a short of time and put the element. So it's fine, it's totally fine to wait until the element is written to the slot. So it's a possible solution. It's very simple and it works pretty good in practice. And in this case, the purple thread must wait until the slot becomes non-empty. So it waits until the yellow one puts 1, so then yellow can finish. And only after that, the purple one proceeds and returns the value located in the slot. Now it returns 1. And here's the question. Are these enqueue and dequeue operations lock-free? Obviously, they're not lock-free because you see in dequeue, we have a blocking part. We wait until the cell becomes non-empty, and in this case, we have blocking behavior. So we don't use any lock here, but the algorithm we just constructed is blocking. But to be honest, even this solution, it works very, very well in practice. So sometimes you don't really need to care about blocking behavior because in this case, one enqueue can block at most one dequeue. So it's not the same as we have with the coarse-grained locking when all operations are protected by the same lock. In this case, if the operation that holds the lock is stuck, then all other threads must wait.
Nikita, could you please stress, do you consider multiple writers and multiple readers for the moment, or one writer and one reader for the queue? Because if we have multiple consumers, multiple producers, you have much more questions about the correctness.
So regarding multiple producers and multiple consumers, nothing will change because still at most only one enqueue and one dequeue works with the same array slot. So when enqueue starts, it performs the increment, so it claims the slot. And when deque starts, it also performs an increment to claim the slot. So different enqueues, concurrent enqueues, they work on different cells, and different dequeues work on different cells. So in case of multiple producers and multiple consumers, the situation is exactly the same. And similarly, one enqueue can block at most one dequeue in this unlucky situation.
If we will use dequeue like this for multiple consumers, couldn't we violate the linearizability of the queue?
No, but here is a small mistake, because dequeue index plus and dequeue index plus they should be replaced with fetch and debts, of course. It's a bug. Concurrent programming is bug prone, and here's a small bug in the presentation.
Okay, maybe we will discuss it later.
But what is your question?
I think we have here a waiting algorithm, but what if the second dequeue will exit its while loop before the first one? So it will observe the second element of the queue before the first will notice it. Is it will be good? Or you just think that the dequeue operations just swapped in time?
So, okay. Here we synchronize enqueue and dequeue. They are these operations are concurrent, right?
Yeah.
So we agree in this. Good. So as they are concurrent, we can linearize them in any order.
Mm-hmm.
And the idea that with this solution, we linearize first enqueue and then dequeue.
Okay.
So first, and that's what we see. First enqueue puts the element, and after the dequeue comes. So this blocking behavior we just added, it resolves the situation when dequeue comes before the corresponding enqueue.
Is it possible that the first thread that performs two enqueues, but when dequeue, we'll see the dequeue of the second element later the concurrent consumer will see the previous earlier element?
I don't think that it's possible, because if you insert the first element into the first cell, you insert the second element into the second cell, and the following dequeue operation, it works on the first cell, so it will retrieve the first element. It can't retrieve the second element first, because we increment the index in the beginning. So we first process the first cell, then the second, then the third, and so on.
Mm-hmm. Mm-hmm. Okay.
Is it clear now?
Maybe. I think it's more. Maybe it should be clarified in the end or in the discussion zone, because reasoning such things without schemes is just complicated. But I believe you are right.
Okay. So this enqueue, this dequeue, they are not lock-free. In particular, enqueue is lock-free here, but dequeue is not. And we want to make dequeue non-blocking. So how could we do that? Let's take a look on the transition state diagram for each cell. Initially, it's empty, it's null. And when enqueue comes, it inserts an element, and thus it moves the state to to element. And when deque comes, if it comes when the cell is in the empty state, it waits for an element to appear. And if it comes and see that, oh, here's an element, it simply retrieves it and finishes. That's the scheme. And in this scheme, deque is blocking. And we can make it not blocking using the following trick. We can add an additional state, kind of poisoned state. So when deque comes and it sees that the cell state is empty, instead of waiting, instead of making this blocking behavior, it can simply poison the cell. So the cell becomes broken, and then it restarts. And enqueue can't put the element into the broken cell. So in this case, enqueue also restarts. And now these transitions, they can be performed concurrently. So deque can perform transition, enqueue can perform transition. They have to synchronize. Here we need to use a compare and set instruction. That's what I mentioned in the beginning. So we can't make non-blocking algorithm using only fetch and adds, because we created blocking one, but we can perform the most of the synchronization using fetch and adds, and further use the compare and set for more tiny synchronization. So now we synchronize not all threads, but only one deque and one enqueue, and in practice, these compare sets never or almost never fail. So now our code is the following. In enqueue, we update the cell state via cast, and in deque we do the following. So our conflict is resolved the following way. So the yellow starts, like in the previous example, it increments enqueue index, and it's stuck for a while now. And then the purple one starts and it increments the deque index. After that, it goes to the claimed cell 0, and it notices that the cell is empty, so it poisons the cell and restarts. After that, when the yellow thread comes to the cell, it sees, oh, it's already poisoned. So the corresponding class that tries to install the element, the cell is still in the empty state. This class operation fails, and thus the yellow thread must restart. So it restarts, it increments the enqueue index again, and puts the element successfully. And after that, if the purple thread continues, it increments the deque index, and now, wow, in the first cell there is an element, so the corresponding class that poisons the cell, it fails, and deque successfully retrieves the element. So it finishes. So maybe we should stop here for questions. Give some time for the attendees.
Yes. Can you show what in such technique the deque index will not go after the enqueue index, and the consumer will go much forward forever?
So now we still assume that the queue is non-empty. It was empty in the beginning, but we will fix it right now, okay?
Okay. So we are still relying on the deque is behind the
yes
producer.
Yeah.
Oh, okay. Then we don't have still questions except the one usual, what you didn't consider any pairs for a moment, but I also answered to our
we don't care about pairs.
Suppose what everything is volatile as a model.
And in practice, everything is volatile here. Okay. Now let's fix the problem you just described, and maybe somebody will ask questions in the meanwhile. So here we had a problem, right? That when the queue is empty, the queue should finish. It shouldn't try to claim the slot, poison the cell, restart, and again and again. So how could we check that the queue is empty? So we can do that. We can do that using only the queue index and end queue index counters. How could we do that? So I will remind you. The queue index, it points to the cell for the next deq operation, and enq index, it points to the cell for the next enq operation. And what we want to check is whether the cell for the next deq operation already contains the element, or should contain, in some sense. So we can simply check whether this cell referenced by deq index is already covered by enq. So we simply compare deq index and enq index counters. And if deq index counter is great, let's do this, because otherwise do this. So when deq index counter is greater or equals to enq index, then the queue is empty. Why greater? Because it's possible that the queue contains one element, then 100 of enqueus come. All of them decided that the queue is non-empty, and all of them decrement deq index. So deq index, in this case, becomes greater than enq index, but it's a very rare, unrealistic case. But we still need to think about it. And also, what is important here is that we must read deq index before enq index. You remember that deq index always increase and enq index always increase. So when we read deq index and then enq index, then at the point of reading deq index, enq index also contains some value. And when we read the enq index after that, it contains either the same value or greater value. So our condition will still be correct. If we read first enq index and then deq index, then it won't work. You can check. Or we can discuss this in the later if we have time. But to trust me, it's important. It's very important to read counters in proper way. And that's why concurrent programming is so error-prone, because you replace the order of the reads, and your algorithm doesn't work, and you don't really know why.
And do you have any reasons why this algorithm has a progress warranty or doesn't have?
We'll discuss this right now.
Okay.
But that's a good question, actually. That's a good question, because it seems like the algorithm is non-blocking. So here's the question. Are enq and deq operations lock-free? So we fixed the blocking behavior, right? Or is this algorithm still blocking? So the intuition says that the algorithm we just constructed is non-blocking, because if enq is in conflict with the deque, then deque can poison the cell and continue. So it seems that it's non-blocking, but it's not lock-free, because it's possible that enq increments the counter, then deque starts, it also increments the counter, poisons the cell, then enq continues, it detects that the cell is poisoned, so it starts from the beginning, it increments the counter, and then the execution goes to deque again, and it can be an infinite process. So two particular enq and deque operations, they may stack. And thus, we can't guarantee system-wide progress. But what can we guarantee? And for such algorithms, there is a special abstraction freedom progress guarantee, and it guarantees that that each operation should finish in a bounded number of steps if we pause all other threads. So if there is no interaction with other threads. So in this case, if we pause enq forever, for example, then deque finishes in a bounded number of steps, right? Because there is no such interaction, infinite interaction between enq and deque. But it's still possible that enq and deque interact in an unlucky way. So just to remind you, lock freedom guarantees that there exists an operation that finishes in a bounded number of steps independently on what other threads do. And the wait freedom guarantees that each operation finishes in a bounded number of steps independently on what other threads do. Okay, so wait freedom is the strongest guarantee. Then lock freedom goes, and the biggest non-blocking progress guarantee is abstraction freedom. But in practice, abstraction freedom is usually it's good enough. And in this case, in practice, the algorithm is fate-free because this cell poisoning, it almost never happens in practice. So maybe we can stop for a minute here.
Well, we don't have any additional questions about the if we are bound to have poisoned cells scattered along the queue, but I think you already showed that yes, it's theoretically possible, and this is the technique of such a class of algorithms, I believe, usual approach. But I don't know. Yeah.
In practice, everything works fine.
Well, I'm interested for myself how such a queue will behave when we don't have a much overwhelming producing elements. So reader most of the time looping around just one or two elements queue. So is it scales well in such a case?
It scales well, but let's discuss this question in the discussion zone after the third talk. Okay, it's a very interesting question actually, and we can do a lot of tricks in this case.
Okay, and the second one maybe to the same discussion area that. Do we have, after all, the scalability because we use classes everywhere?
We do use classes, but they are uncontented classes. I mean, they almost never fail. So if in enq, let me remind how the algorithm works. In enq, when we do a class, it almost never fails in practice. So we perform an unconditional fit test extraction. never fails, and then we perform cast that almost never fails. And in Deku, Deku almost the same way. The Deku increments the index, and after that, it almost never poisons the cell, so it simply retrieves the element. So we do use classes to synchronize enqueue and dequeue in such corner cases, but in practice, these classes are just for the corner cases. We don't pay a lot for them. We don't restart from the beginning every time, as we do with the classic Michael Scott algorithm, for example.
Okay. I think.
Yeah, so let's move forward because we don't have a lot of time.
Yes, okay, let's move forward. Yeah.
We have time, then we discuss it. So now the only question that is uncovered is how to implement this infinite array. We assumed that we have an infinite array, but we don't, actually, right? There is no such construction in the standard library, in any library. And we need to emulate the infinite array somehow. And the idea is that we'll use the Michael Scott queue for that. We'll use a Michael Scott queue of segments. So instead of storing each element in a new node, we'll have fixed sized segments and linked list of them. And each segment has an ID, and the size is fixed. So when we need to go to some cell, we know which segment we need, and we know which cell in this segment we need. And now we want to modify our enqueue and dequeue operations to use this construction. And the idea is the following. In enqueue, we first read the last segment. Because we want to put, it's likely that we'll use the last segment. And only after that, we perform the enqueue index increment. And then we need to we do know which segment we need. We need segment with the ID, I divided by segment size. And we need to find this segment, following the next pointers in this linked list, starting from the segment we have read in the beginning. So we find this segment, and after that, we also update the tail segment. We move it forward. We do this atomically because it's possible that it's already updated. So in this case, we don't do anything, but we almost move the tail pointer forward. It's kind of the same as we did for the Michael Scott queue. And then we have the segment we need, and we know which cell we need, and we work with it. And exactly the same transformation should be done for dequeue. And that's how an infinite array can be emulated in practice. And this find segment invocation, it also creates new segments if needed, because it's possible that there is no segment with the required ID. So in this case, we just try to create a new segment and add it to the list. And if we can't add it to the list, then it means that there is already a segment with this ID in the linked list, and we simply use it. And as I already told that this move tail forward and move head forward updates the references only if the ID of the updating segment is related than the current one. Otherwise, we don't need to move tail or head forward. That's how it works. Okay. Maybe we have a minute.
Well, we don't have much questions more, except the one that if 64-bit counter is enough to be an infinite.
Yes, it's they're practically infinite.
Okay. And I believe also that the moving ahead further will be based on the Java abstraction of garbage collection.
What do you mean?
Because if we are manually managing such a blocks, we'll have a more complicated problem with freeing used segments, because we may have late consumers who are still holding pointers to some earlier segments.
Yes, you're right. Here we assume that we have garbage collector, of course, because if we don't, if we don't have a garbage collector, we do need to think about memory management, and it's a complex problem itself. So just for simplicity, so it can be solved here. Not a big deal, but we don't want to think about memory management right now. We just have garbage collector, it does the dirty work, and we're happy with that.
Okay, we still didn't come with new questions, so I think we should move.
Super, so let's move forward. Forward. And so yesterday we talked about building synchronization on using mutex. It was so easy, right? It was not like the algorithm we just discussed today. It was easy to make any sequential algorithm correct in the concurrent environment by guarding all the operations via mutex. It's easy to maintain such a solution. But the problem is that coarse-grained locking never scales. And at the same time, when we create a non-blocking algorithm, it can be really scalable, like the queue I just presented. But it's hard to implement because you need to think about a lot of current cases. You need to think about reading the counters in a proper order. You need to implement this infinite array, and so on. So it's hard to implement this data structure. It's hard to test it to make sure that it's correct, and to also need to maintain this code. And sometimes you don't want to do this. And here's the question: what should you choose? And of course, it depends on whether you need just correct behavior or you need good performance. If you need just the data structure to be correct, you use mutex. And when you need a really good performance, you usually use non-blocking algorithms. But is there something in the middle that is as easy as mutex, but is scalable? And 12 years ago, there was a paper on the flat combining technique that essentially makes it possible to make any sequential algorithm non-blocking, but also maybe not scalable, but much more efficient than one with the coarse-grained blocking, with the mutex. And the idea is very simple, actually. So we will use mutexes. Okay, we will use logs. And the data structure, the sequential data structure that will be under the hood, it will be protected by these global mutex. And when a thread comes and it wants to apply an operation, it tries to acquire this lock. And if the lock has successfully been acquired, then this thread becomes a combiner. So this thread will work with the sequential data structure. And the idea is that other threads that hasn't acquired the lock, because the lock is already held by another thread, they, instead of waiting for the lock, they publish the operation to a special place and say to the combiner, hey, could you please apply my operation? Because you already have the lock, so it's not a big deal for you to apply the operation, because acquiring the lock, using the lock, it takes time. We need to perform a lot of synchronization for that. And in this case, it would be much, much better because you don't need to acquire locks every time. Okay? So the combiner, after it applies its own operation, it also tries to help other threads with their operations. And all the other threads that are not combiners, they either wait for the result after they publish the operation to the special place. They wait for either the result or for the lock to become a combiner. Let's take a look at an example. Let's build a queue using the flat combining technique. So we'll have an array, and threads will publish the operation to this special array if they can't be combiners, and they will just try to push the operations to a random slot. Okay. And we'll also have a mutex that ensures the exclusive access to the sequential data structure under the hood, and the thread that holds the mutex, it's the combiner. So we have a sequential queue here. It's empty now, and we have 3 threads: the green one that performs NQ1, and the yellow one that performs DQ, and the purple one that performs NQ. Let's see how these threads will interact with each other. So when, for example, the green thread starts, it tries to become a combiner, first of all. And as the lock, the mutex was unlocked, so it acquires the lock. Now it's combiner, and it's combiner. And after that, the yellow thread comes, and it can't acquire the lock because the lock is already held by the green thread. So it puts the DQ request into the array and waits for either the result in this array slot, or it waits for the lock. And after that, for example, the green thread, it continues, it inserts the element, and it goes through the array to help the others. So it goes to the first cell, to the second cell, to the third, to the fourth. Now it sees, wow, there's DEC operation. I should help it. Why not? So it helps the yellow thread to perform its DEQ. Now the queue becomes empty, and in the cell it stores the result of the operation. It stores 1. And then the yellow thread finishes without acquiring the lock, right? Because the green thread just helped the yellow one with its DEQ. So the yellow says, wow, I didn't have to acquire the lock. That's good. And then let's say the purple thread starts. Oh no, then green continues, then purple thread starts. And as the lock is still acquired by the green thread, the purple thread puts its NQ operation into the array slot, but the green thread it won't it won't go over the array again. It will just check the last slot and finish. So it will say, "Oh, I helped as much as it was possible. Then I'm no longer a combiner. I need to go." And after that, the purple thread notices that the lock is no longer quiet. So in this case, the purple thread, it becomes the combiner, and it updates the queue. It also goes over the array to help the other threads, but there's nobody to help, and it releases the lock and finishes. That's how the flat combining technique works. And so the main idea is that we don't need to wait for the lock. Instead of that, we put our operation description to some place, and the thread that holds the log, it helps you to finish the operation. And also, as we don't really wait on the log, we don't need proper mutex implementation. It can be organized in the following way, just using a single logged register. And when we try to acquire the log, we try to automatically replace the logged field from false to true. And when we release the log, we simply put false to the logged field. Okay. And to sum up the flat combining technique, it's really easy to use because once you implement it, you can apply it to any data structure. So you can make any sequential algorithm correct in the concurrent environment because we use the global mutex to synchronize the threads. But the solution is faster, especially if you have quite a contention on the data structure. And sometimes it's really hard to create a non-blocking version of your sequential algorithm. For example, it's hard to make a non-blocking priority queue. So priority queue based on flat combining, it will be the fastest one. And also, sometimes, for example, in graph algorithms, it's possible that it's cheaper to process operations in a batch, and thus, when a thread becomes combiner, it can collect all the operations and process them in a single batch, and thus improving the performance. But of course, all the operations, we still apply them sequentially. So we pay less for the synchronization here, but we apply operations sequentially. So flat combining, of course, not really scalable, but it's still a very, very good technique that is used in practice. And we don't have a lot of time. We have a couple of minutes. So just to sum up, today in this talk, we learned a new fetch and add instruction, and we used it to create a really fast queue algorithm, which is actually abstraction-free, not log-free. And we also discussed the flat combining technique, which also can be used to make any sequential data structure concurrent. And as in the previous talk, I also prepared some task segments so you can implement the queue and the flat combining if you go to this repository. So that's it for now. And Dmitry, maybe we have questions.
Well, we didn't have questions in the chat, and we ran out of time for our slot. So I think we will discuss later in the discussion zone, or maybe in the chat if you see it, and questions will come. Also, I just a quick question about flat combining. So the operation what should want to perform its operation and waiting on the log should be organize a loop combining try log and check its slot if it's already fulfilled. Yes?
Yeah, you understood it correctly. We just need to do anything to loop in which we try to invoke try log, and after that we check whether the slot contains the result, and we wait either for the log does or for the result.
Okay.